In this lecture, we will cover acids, bases, and pH. So when we talk about acids and bases, what we're really talking about is how many hydrogen ions a solution has, little H pluses. Okay, you'll see these a lot. Water molecules in a solution may dissociate, which means break apart, into positively charged hydrogen ions, those little H pluses, okay, and negatively charged hydroxide ions, OH minuses. You'll see these a lot too. Okay? So if you can imagine, this molecule of water, H2O, has now broken in half. We have an OH minus and an H plus. Okay? So this is how water works. All right, so just water all by itself. You've got a bunch of H2Os, and several of them have split into H pluses and OH minuses. So when we talk about acids and bases, we're really asking how many hydrogen ions, how many H pluses are in that solution. So we've taken our water, okay, just regular old plain old water. If we add an acid to that water, okay, so for example, hydrochloric acid. Okay. Now yes, the name itself, hydrochloric acid, it tells you what it is and what it does and how it works. But some are a little less obvious. So here's what happens when you add an acid to plain old water. Okay? You are really adding a proton donor. Okay? Because that's what a hydrogen ion is. It's really just a proton. Okay? So the number of hydrogen ions in a solution increases when you add an acid. So if you look at this molecule, HCl, okay, when we put that into water, it dissociates, it breaks apart into chloride ions and hydrogen ions, H pluses. Okay. So if we go in here, and if we were to add these up, okay, you would have quite a few hydrogen ions. Okay. You would have more hydrogen ions than you would hydroxide ions. Now, if we did the same thing with water, but now we added a base. So here's our plain water again. Okay. Here's our base. Okay. Bases are going to be hydrogen ion acceptors. Okay. Some of them will be hydroxide donors, so we'll add OH minuses instead. So bases are a little more complicated because we have two choices. But either way, we're either going to remove some of the hydrogen ions or we're going to add more OH negative ions, hydroxide ions. Either way, hydrogen ions decrease in water if we've added a base. So here's our base. Okay, NaHCO3. So when you put this in water, we're going to dissociate, we're going to split in half. We'll have sodiums and we'll have HCO3. So we can see in our picture we've still got regular water molecules, okay, but we've got our little sodiums. They're kind of all by themselves. They're just hanging out. Where did the HCO3s go? Here they are. Oh, what have they done? They've attached themselves to free-floating hydrogen ions, which means the overall concentration of hydrogen ions has decreased. That's how a base works. Okay, you are either going to remove some of these hydrogens, okay, you're going to bind to them, or you have in some instances where you have certain bases that will actually just add more OHs. Okay, so here we go, pH scale. Okay, your pH scale ranges from 0 to 14. And again, we're really just measuring how many hydrogen ions we have in a solution. Now the pH scale, it looks pretty simple. We're going from 0 to 14, just whole numbers. Okay. That's a little bit more complicated than that. This is a logarithmic scale. Okay. So actually each number is 10 times different than the previous or the next number. So if we go from a 4 to a 5, okay, a 4 which is an acid, is 10 times more acidic than a 5. Okay. And a 5 is 10 times more acidic than a 6. Okay. And if we did bases instead, a 12 is 10 times more basic than an 11. Okay. So we're not just adding a few more hydrogen ions, okay, or removing a few more hydrogen ions. We're doing quite a bit. So we can see our gradient here. We have a ton of hydrogen molecules the more acidic we go. We have a ton more base molecules the higher we go. So we have 3 options. You could be an acid, you could be a base, or you could be neutral. Okay. Now we started with water. Water is neutral. Right in the middle, good old 7. Okay. Good old 7. What do we mean by neutral? Okay. We've discussed neutral atoms, right, having the same number of protons and neutrons. It's a similar idea. Okay. If you are a neutral solution, you have equal parts hydrogen ions and base ions. Okay? So your H pluses equal to your OH minuses, or your other base ions. Okay? Now, water is about the only pure thing that we can come up with, because it really all started with water. Do we remember if we go back? Okay? Water is nothing but H pluses and OH minuses. It should make sense that these would be equal. Anything else that you add to water is going to change this slightly to where you would either be acidic or basic. Okay? And another term for basic is alkaline, or alkaline, however you want to pronounce it. It's a popular term. So if you are an acid, if you are an acidic solution, you fall below 7 on the pH scale. We're familiar with many of these. Okay, stomach acid, again, it's in the name. It's a little on the nose. But tomatoes, coffee, even milk. Okay, these are all acids. If you're an acid, you have more hydrogen ions than you do have base ions. Okay. And then we could be above 7 on the pH scale. If we are above 7, then we are a base, or we are an alkaline solution. Now we would have more base ions than hydrogen ions. Notice that we did not say 0 to 6 and 8 to 14 for acids and bases. A 6.9 is still an acid. A 7.1 is still a base. Okay, so we refer to it as being less than 7, greater than 7, or equal to 7. Now, why do we care? Because your body, all that water, you are a solution. And acids and bases in too great a quantity can cause problems. So we have what are referred to as buffers, or buffer systems. Okay? The job of a buffer is to resist changes in pH, okay, regardless of what we're doing to the solution. And so this is kind of a weird idea. And put you a little note here as well. All right, this is kind of a confusing topic. You might want to go back and look over this a couple times. So one of the common misconceptions about buffers is that a buffer would try to neutralize a solution. And that's not how they work at all. Okay? So you have buffers that's whole job is to keep a solution in a pH of 3, which is very acidic. You have other buffers that their job in life is to keep a solution in a pH of 12, which is very basic. So we're not trying to neutralize anything. We are trying to keep the pH consistent at whatever it is. Okay? So your blood is slightly basic. Okay? Your blood should be anywhere between a 7.35 and a 7.45 on the pH scale. So just a little bit basic. Okay? We have a buffer system that allows us to maintain this range, the 7.35 to 7.45, okay, regardless of what we're doing in our body. And most of the time it works. Okay, most of the time. However, sometimes we do go away from good old homeostasis. Anything below a 7.35, say we've got down to 7.31, we consider that an acidosis. Our blood is now too acidic. If we've gone a little too high, now we're maybe at 7.48. This would be considered an alkalosis, and our blood's gotten a little too basic. And your body does have ways to fix this, okay, normally. So as long as your body works normally, we can fix this. Okay. And your body actually does this all the time. Okay. So these first two reactants should be familiar to you, carbon dioxide and water. Okay. You know that your body is full of water, and you know every time you breathe in oxygen, we use it and we turn it into carbon dioxide. So this is very commonly found in your body as well. We can take that carbon dioxide and water, we can combine them to make something called carbonic acid. Again, the name gives it away. It is an acid. Okay. That carbonic acid can then be dissociated into hydrogen ions and bicarbonate ions. Okay. You've already learned that a hydrogen ion is an acid. Now I'm going to tell you that bicarbonate is a base. Okay. Your body can regulate the concentrations of these three atoms and molecules to help us keep our pH in our normal range. So, I'll go back. If we end up with too much hydrogen, okay, your kidneys can work to get rid of that. Okay. If we end up with too much bicarbonate, our kidneys can help there as well. We have other ways. We won't go into a whole lot of detail. Okay. But your body can regulate the concentrations of these three atoms and molecules to make sure that our blood pH stays at that 7.35 to 7.45 range. Now, we did mention that sometimes things do go wrong. Sometimes we do fall below 7.35, and that would be considered an acidosis. We could go above 7.45, and that would be considered an alkalosis. I did just mention your kidneys are involved in this. Okay. Your lungs are also involved in this. Okay. Which should make sense. If we go back, carbon dioxide, we know that we get rid of carbon dioxide through our lungs. Okay, so we could also just get rid of carbon dioxide. We refer to these as either metabolic acidosis and alkalosis or respiratory acidosis and alkalosis. Again, we won't go into too much detail, but if you want to take a peek and read some of these signs and symptoms, okay, you can see just what a big deal this really will be. Alright, that concludes our discussion on the pH scale, acids, and bases.